on that note of what identically distributed data means, I think that's, if I had to pick one like entry point to what is often missing in one's intuition, if you weren't told about it to understand statistics, it's this idea of a data generating mechanism. You're used to having a data set in front of you, and it's just a bunch of flat numbers, and magic happens, and then you get some sort of answer, some inferential answer at the other end. But a lot of statistical theory is based on this idea that every row, let's say, in your data, if the rows indeed are independent from each other, it just came from some process, some abstract process, and that data point could have turned out to be different in some way. There's some natural variation. Indeed, there's a distribution of values that any one of your observations could have taken. So there's a thing, this abstract thing that is generating all of your observations at the time that you got the data set that you have. And we will talk about this concept later, but IID, independently and identically distributed data, means independent. The individual rows in your data, say, are not related to each other. And identically distributed means that the process that's generating them doesn't change until the data set is fully produced. Again, with something like time series, that doesn't fully hold. There's other assumptions that you can say, but in most cases, people have data that could be thought of as generated by this data generating mechanism. The visualization that I'm about to show you is one that I made today. So this is my first time trying to explain it. We're going to, in a certain sense, cover most of the material twice because the slides would do it, but I think that the visualization gets to many concepts at once. We'll see how good it is, so I'll appreciate your feedback. You can see my screen, right? You're seeing RStudio. Do I have that right?
That's right. Yeah.
Great. Yes, we see the screen.
Okay, cool. So I'm going to generate some data. Here I have, my data is just going to be one dimensional. It's going to come from a normal distribution centered around 0. Most of the normal distribution is had by the time that you're out to 3 standard deviations on either side. And then this is going to show the density. There's a reason we call it density, not probability. So this is the truth. This is the real distribution that my data is going to come from. And the height, what's meant by the height here is not probability, because strictly speaking, for some continuous distribution like the normal distribution, the probability is 0 that you pick any one value. It's more like the probability that you get any one value is proportional to the height of this. So it's a distinction that maybe you don't really care much for, but for things like dice that have discrete finite outcomes, they have a proper probability. Density doesn't. It's similar to that, but the way we treat this is the probability is the integral between a range of values. So never mind that. For the future, we can call it just probability. Who cares? So this is the data generating mechanism, the thing that's going to make some observations. And I'll draw some points now. So this is 30 observations. It doesn't capitulate the whole data generating mechanism itself. We can see that there's some points over here and there's a little cluster over here. And, it's not exactly a normal distribution. And there's something called a kernel density estimator that just puts a little pile of sand around each of our points. If you wanted to estimate the distribution of what we had, it would look something like this. We know that in reality, the thing that made it, if we drew like tons and tons of data, it would look just like this yellow curve. But that's not the data we have. What we have are the blue points. And let's say that we're just trying to understand one thing about the truth, the yellow thing here, which is the average. We know, of course, that the true average, hold up, the true average is here at 0. And it's implicit to the normal distribution here, but I've just put the point for clarity. Now, I don't know ex ante that my data is generated from a normal distribution centered around 0. I want to know what the mean is. And let's just say I just don't know what it is. So I can do an estimate and make a confidence interval. We'll compute tons of these. What this diamond here is the empirical average. I summed up all the values of my points and divided them by the sample size, and that's what I get here. And from the central limit theorem, we know that the distribution of the average, that is, the average of all these points is itself normal. It doesn't matter that my data generating mechanism here was normal. It could have been anything at all. We know that this thing is normal, and we also know it depends on the variation, natural variation in the data. It depends on our sample size. But there's a formula for what the standard deviation is. That's the sort of thing that we have to estimate. But let's say that I did estimate it, and I'm going to use the standard deviation to put these bars out here that give me an estimate of this whole estimated distribution. There's only two things to know. There's the mean and there's the standard deviation. And once I have the estimates of those things, I can estimate where I think the mean is, as well as all of the variation in there. So one second, Shisha, I'll get there. The main thing that statistics is trying to do is, if we're trying to estimate something like the mean, there's the truth that you don't have. The truth is the thing that generated your data in the first place. And using your data, you can get an estimate of the truth. And because of asymptotics, we know something about, if I gathered this data many times, my estimate is going to cover the truth with some reliability. And we can control the reliability by having wider bounds around this if we would like. So let me just, here, the colors are maybe not exactly to my liking. So this is the same thing again. The animation that I want to do is to show how this picture looks different if I got a fresh new data set, just to bring home that the variation implied in the data generating mechanism gives me a different picture. So my estimate here is a little bit high, but it just so happens that if I use the central limit theorem and I have these bounds that themselves are estimated, it's going to cover the truth. I know that this isn't exactly the truth, but the confidence interval will cover it. So I can do it again. Okay, I got a different value for the mean, different data points. It's actually pretty good this time. So just as the data has a sort of like, temperature to it, this Brownian motion that keeps fluctuating, my estimate itself also changes, but I can control just how often my estimate, plus or minus some bounds, is going to actually cover the truth. In real life, we don't get to see the simulation. We only get one data set, unless you're, usually it's expensive or difficult to get data, so you can't do it. But this is the picture that we only get one frame of, but this is, if we had access to the data generating mechanism, we'd be able to do this all the time. And if I were to do this enough times, let me see if I can get one. Oh shit, it was the previous one. Every now and then, just by chance, my estimated mean, and my confidence interval is not going to cover the truth. This is called a false positive. I somehow have too much confidence that this value is not zero. So this will happen, and we can, by adjusting these bars, we can decide how often we're going to have one of these false positives. So we will review all this in a little bit, but it sounds like there's a couple of questions, and I want to pause for those.